In this lecture, we are going to prove orthogonality of characters. So let us start with some facts which we want to prove. So first is the notation. So this V star is the dual vector space. So set of homomorphisms from V to complex. So this is dual vector space. And then if you tensor this with W, you get this another vector space which is set of morphisms from V to W. So two results we need to prove first. So first is the character of this dual vector space is the conjugate. So obviously you know the character actually lands in complex numbers, so you can take conjugation. So this is the conjugate, so star becomes a conjugate. And second is if you take the character on this vector space which is home V to W, this is just product of two things. So conjugate of the first vector space here, you see this is conjugated, and the second is just W. Again, these characters are elements of complex numbers, so you can take conjugates. So by this we essentially mean this, we corresponding to some element G, and this, because character is nothing but you whatever representation matrix you have here, you sum up the diagonal entries. So let us prove this. So first you fix base for vector space V, and then you have the corresponding matrix with respect to base A, you denote it by M. And for the dual, if you want to consider dual of this, then you have to take the inverse transpose. So this M minus T means inverse transpose. But the thing is, if you take transpose, it does not change the trace of the matrix, because the diagonal elements remain fixed if you take transpose. So if you consider the dual vector space, this is trace of this matrix here, because this is the matrix corresponding to this. So corresponding to any base A, you can talk about the dual space. So this is just linear algebra. So these two equalities come from linear algebra. And so for the dual, you have to talk about trace of this matrix. But we just said the transpose doesn't matter, because transpose doesn't change the elements on the diagonal. So this is just trace of the inverse matrix, because for character you're just worried about the trace. And inverse matrix trace is nothing but G inverse. So this we have shown in previous lecture, and then this is also shown in previous lecture, that this is just conjugate. So this is it. So this again follows from linear algebra, and yeah, just follow your nose. And for the second part, you know that you take any two vector spaces like this, this is just product, and this again we have seen in previous lecture. So this is just the product of two elements, this chi of V star times chi of W. But this thing is right here, you can see that, because V star becomes this conjugate, and this thing is right here, because this V star tensor W is just this home CVW which comes right here. So this side is exactly this side, since this is same as this, and this is same as this from part 1. So this is same as this. So now we come to defining the inner product of characters. So consider the space of complex valued functions. You're going from the group to complex space. So then you can consider a subspace of these complex valued functions, and this subspace is precisely which satisfies some relationship like this. This KGK inverse is f of G for all G and K in this group G. So in other words, these are precisely those functions growing from G to C. So these functions which are constant on conjugacy classes. So for every group, you have seen in elementary group theory that you can form these conjugacy classes. And these functions which look like this, which are constant on conjugacy classes, we call these functions as class functions. So we call these functions as class functions, and we denote them by this math cal C and G. So basically every group you can split up into conjugacy classes, and these functions then act on conjugacy classes. Because they're constant on conjugacy classes, so the number of conjugacy classes is precisely the dimension of this, because on every conjugacy class this function is a constant because of this relationship. So for any group you can form a list of conjugacy classes for a finite group G, and the total number of conjugacy classes is this, then the dimension of this CG, that is dimension of class functions. So once you have such a class functions, you can make into a Hermitian inner product space. So by defining these two functions f1 and f2, so this f1 and f2, they go from G to complex numbers and both of them satisfy this relationship here, then you can form a Hermitian inner product like this. So obviously, since you're landing in C, you can take the complex and sum it over all elements of the group. So if you have forgotten Hermitian inner product, let us just quickly go through its definition. So Hermitian inner product is a map from vector space to complex numbers. It satisfies three properties. So the first thing is that you take a and b in complex numbers, and if you have something like this ax plus by comma z, then you can take this a and b out. So you have a conjugate and b conjugate y and z. So you look at the conjugation here. So you have conjugation in the first variable, and if you a and b are here, you can conjugate it. And if you're in the second variable, you have ax and b, this ay and bz here now. Now again you can take a and b, so notice that there is no conjugation here. So in the second part there is no conjugation, in the first part there is conjugation. So this is what is called sesquilinear. The second thing is Hermitian inner product. This is just xy is same as if you go yx, but now you have to conjugate it, and then you have positive definites. So this is greater than 0 for all non-zero vectors. So we are now going to prove this big theorem. So if V and W are two representations of G, then the dimension here is just this inner product of the characters of two spaces. So notice I'm putting W here and then V here. So because this dimension is going to remain same if I put W first and V then. So this is actually the same as if you're going to do this. So nothing much changes. But when we do the proof, this is what we are going to end up proving. And this equality comes from the fact that this thing is also equal to our dimension of home, but now going from W to V. So this theorem is crucially depends upon this lemma. So if U is a representation of G, then you can talk about this U superscript G. This is standard notation for all the elements which are fixed by G. So all the vectors in U on which this row of G acts, you still get U. And then dimension of U of G is just this. This is dimension of U of G. So if this is the dimension of U of G, then we can prove this theorem. So let us go through the proof of this theorem. So now let us prove the theorem. So I'm copying this right here. So you're taking inner product. So this is this definition we have copied right here. Now we use the first result here. So it doesn't really matter because this is just a product of two spaces. This is just two complex numbers. You're taking product of them, so they commute. So you can do it like this. And this is precisely this. So we are putting home here, and this becomes the dimension which comes from here. So this is precisely the elements which are fixed by G. So because the definition of home GVW is precisely those maps. So this is precisely those maps, say varphi in home of VW, on which when G acts on this map, it still gives you phi. So this is exactly the definition here. So because now we are writing this for our this home GW. So these are precisely those maps which are like this. They lie in our this home morphisms from V to W, which are fixed by G. So after this theorem, we can prove certain corollaries. So this is the most important corollary for which we recorded this lecture, that is orthogonality of characters. If chi and chi prime are two characters of irreducible representation, so say this chi and V, and for V prime you have chi prime. So then this chi comma chi prime, this inner product, is this Kronecker delta function, which is basically 1 if V and V prime are isomorphic and 0 otherwise. So this just follows from the theorem here and Schur's lemma, because if V and V prime are isomorphic, then we know that, so instead of W we are writing V prime. We know from Schur's lemma, so this dimension, if V and W are isomorphic, this will be 1. So that is what it says here. So if v and v prime are isomorphic, this chi v and chi v prime, this is going to be 1. If they're not isomorphic, this is going to be 0. And that is what it is. It is 1 if v and v prime are isomorphic and 0 otherwise. So follows from Schur's lemma here. So these two are isomorphic, then we know the dimension is v and w are isomorphic, we know the dimension is 1. And if they're not isomorphic, this dimension is 0 from Schur's lemma. So now we come to a very important remark. So say v1 to vr, this is a complete list of non-isomorphic irreducible representations of some group G. Then you can talk about irreducible characters of G. So these irreducible characters are precisely which are associated with this irreducible representation. So these are called irreducible characters. So corresponding to v1, we have chi of v1. Corresponding to v2, we will have chi of v2. Corresponding to vr, we will have chi of vr. So let v be any representation and say ni is this dimension from v to vi. So dimension of these morphisms. So then by Schur's lemma and Marshke's theorem, we can actually write this vector space V as this decomposition. So this is very important. So you can always decompose V into this irreducible components, where each this ni is the dimension from this morphisms from V to Vi. So once you have this, you know that you, for any two vector spaces, if you have their direct sum like this, you can sum up their characters. So this we showed in the last lecture. And so therefore you can sum this up. If you start summing this up, you will get this ni chi of Vi. Now since chi of Vi are all orthonormal, so this we have already shown orthogonality of characters, because each of these Vi is a non-isomorphic to the other one. So therefore all of them have to be orthonormal. So then if you take this chi v comma chi vi, then it just will give you ni, where ni is this dimension. So because you just add the corresponding vi terms ni times. And if you take chi of v for this vector space v, you take the inner product like this. For this vector space, it's just going to be summation of ni square. So these two are important observations which one should remember for representation theory. One is this, and then obviously this gives you this and this. So these two just follow. So now because of this observation, we can now prove another important theorem, that two representations of G, so they are given as rho and rho prime, these are isomorphic if and only if they have the same character. So notice that character doesn't have much information, it is just a complex number. But we have this powerful theorem that now these two representations are the same if they have the same character. So first, in this direction, we already know that isomorphic representations have the same character, because you land up in similar matrices which will give you the same character. So this we have proven in a previous lecture. Now we are working in the opposite direction. Now suppose that we have the same character. So then you can decompose rho and rho prime like this. So both of them, so instead of v1 we are writing rho 1, but for this ni here we are writing chi comma chi 1. Essentially we should write it as chi comma chi v1, but this is easier to write because this is precisely what gives us ni here. So this rho 1 is v1, this is n1, so this rho r becomes vr, this becomes nr, and both rho and rho prime, which you can think of as vector spaces, they both decompose like this. So rho prime will decompose like this, rho will decompose like this, and therefore both of them are equal. So now another corollary. So say let rho be a complex representation of G. So over complex numbers, and character is chi, then this rho is irreducible if and only if this chi, this inner product is 1 of chi with itself. So first direction obviously follows from the orthogonality of characters, because it's a complex representation, it is irreducible, so both of the vector spaces have to be the same, and if they are the same, you immediately get 1 from here, because both the vector spaces are the same, because it's irreducible. In the opposite direction, we have already seen that this chi, you write it like this. So where this chi I means that this is corresponding to vector space vi. So we are just copying this here. So this thing we are copying right here. So this thing we have copied here, but instead of chi of vi, we are writing chi I. And now we are saying that, okay, we are working in opposite direction, so that is this inner product is 1. So this implies that the sigma ni square is 1. So that is because this is this. So this we are copying right here. Now this can only happen that there's only one of the elements here which is 1 and every other ni is 0. So there is only one ni, say some nk which is 1 and every other is 0. So this can only happen if chi is equal to chi of k for some k, and this makes chi irreducible, because to get just a single one it has to be the case that there are two vector spaces of the same. So this so making chi irreducible or the vector space irreducible, because you can have only one of the inner products as 1 and every other inner product is 0, and where their inner product is 1, then you are back in this theorem. So this is 1, so that means the spaces are isomorphic, so there has to be only one of them. So the only thing now left is to prove this lemma. So again, recall u superscript g is precisely those elements of the vector space u which are fixed by g. So this is also written as gu is equal to u. So then you can talk about dimension of u of g. So first thing is we need to make sense of this term. So first you write phi of u is just this 1 over the elements in the group G, and then you're summing it over rho G times u. Then immediately from this you can see the trace is this. So because you will, for every matrix here, this rho of G denotes a matrix, you're just summing up the elements on the diagonal, and then you can sum up all these elements to get this. So that is it. So there's nothing much. And this is precisely why we have this, is because this is the same as this, as you can see. So now again you can see what is dimension of UG. This is just precisely the trace of the identity matrix. So because for the identity matrix you're going to have 1 on the diagonals and 0 everywhere else, so you can add them up to get the dimension. So this is trace of the identity matrix. But immediate computation shows that this acting on this u of g will just give you the identity matrix, and this is precisely because now if you're acting on u of g, so this is u, so this thing becomes u. So if this is u, you sum it over all elements of g and then you divide by that number, you are still going to get u. So you will still get u. So therefore this phi restricted to u of g is the identity matrix. So now we also can show that this, if rho of h acts on phi of u, you still get phi of u. So that essentially means that this phi of u lies in u of g. So rho of h acting on phi of u still gives you phi of u. This because you can change the variable here. So let us do this. This is you will just have this, you have the summation, then you have rho of h, then you have rho of g, and then you have u. But this you can combine to have hg, and then you, instead of g here, you can write hg and g. So then this again becomes an element of phi of u, because this looks exactly like here. You just have changed the variable from g to hg. So this shows that phi of u is u of g, and that completes the proof, because now we have shown that dimension of u of g is just this trace. So this trace of our identity matrix, but this has to be equal to, this is equal to our trace of phi because of this equality here. So this one ug is coming right here, this is coming right here, and this trace of phi is precisely what we want to show here, which is the end result here. Obviously this you can write as 1 comma chi, because you put 1 here and chi here, this becomes this. So that is the end of the story.